Welcome back to Gabversity, where facts care not about your feelings. For example, facts don't care, Miss Bombshell, hello, that my computer just decided to die to save battery power, and it drives me crazy, but that is life. What are you going to do about it? So, I have to load it up again. And then we're going to talk about astronomical units. This is more of a serious lecture today, and we're going to talk about how... Hey, lovely to see everybody. We're going to talk about how telescopes gather light, cameras record images, and spectrographs spread light into spectra. All right, so I was thinking of getting my friend. I don't know if you know him. His name is Al-Asad. I want to introduce you to him, and he's a very nice guy. So are you ready? Hello.
Hello, I am Al-Asad. Lovely to meet you all. Hello, Supernova. I hope you are very well. Is that okay, Gabsmack?
Yeah, that's good. All good in the hood. So we'll get him to read a bit for you.
Okay, I will read some of the lecture for you. You will discover cameras record images. Is that right?
No, how cameras record images.
Sorry. How cameras record images. Hello, Supernova. Lovely to see you. Welcome. Welcome, my dear. And spectrographs spread light into spectra. You are ready to understand why astronomers make such efforts. Here you will find answers to some important questions. What are the questions, Gab?
Well, the questions are, what are the type of spectra you can observe?
What are the type of spectra you can observe? Very good. I am very happy to meet you all. What can you learn from spectra of celestial objects?
So there you go. So now that is how our course begins. And yes, I am sitting up here in my room because honestly today I could not be bothered. It was just one of those days. What is it today? Saturday? I'm working tonight in a few hours until the next morning. And I just can't be bothered. I was supposed to do some physics. Yeah. All right. So we'll go back to Al-Asad.
Thank you very much. Lovely to see all of you. So, as we will say, forgive the mess of Gabsmack's room. He is normally messy, actually. I will not travel to the great Satan.
I think he's talking to me.
Okay, you answer.
I would love to come to the US, my friends. I would love to come, bro. And the plan is to come there and do my book tour. That's going to be fun.
Yes, maybe I will come to the great Satan if Gabsmack is going. For him, I will be happy to consider.
Well, I wasn't asking you.
Okay.
All right, so let's move on to the next part.
Overview. You will be considering what you can see with your eyes alone. Oh, Al-Asad, you're annoying. Who was that?
That's Pompous.
Yes, Bombus. This boy is a very interesting. I'm not a boy, I'm an old man. This boy says he is an old man. Okay. We will be considering what you can see with your eyes, or what you can see aided by telescopes and astronomical instruments. Simba is my cousin from Africa. I am from Asa'ul Ada. Nice to meet you. Also,
so there you go. That is our friend Al-Assad. He's a lovely guy. And he's enjoying this astronomy. Pompous tends to get, he doesn't really focus. So when it comes to serious lectures,
get on with it. This is a Bombus. Very good. You will learn how the instrument called a spectrograph spreads and sorts light according to wavelength to form a spectrum. Bombus is a very interesting person. Hello, National 90. You are a very good friend of Gabriel. So, Even though you are an infidel, you are a friend of mine.
Man, please don't be rude. Be careful. I'll ban you from the public scopes.
I apologize. I will call him disbeliever. Ah, hello, disbeliever. You are a lion too. I am very glad to know you. Okay, this topic marks a change in the way you study nature. You will be learning about modern astrophysics that links physics experiments and a theory to astronomical observations, and thereby understand why the spectrum of an object can be so informative. The lion is always lion. Is you black? You is what you is. And thereby understand why the spectrum of an object can be so informative.
No, as you can see, I am brown.
And I am Arabic. التكلم العربية الطلاقة يا أولادي.
There you go. Lion-hearted. Absolutely. So,
hello again. We will do astronomical observations. I believe, Gabsmack, you will be traveling 6 hours to the observatory and taking all of your students from Gabversity with you. Is this correct?
this is correct. I hope you guys are going to come with me in a month. We're going to head down to the observatory.
Ah, down to the observatory. This is great. What will you be looking at? God or the devils?
Probably both.
Okay, then it will be good. I look forward to watching the scopes. Yes, you will go on a field trip all the way down under in Satan Down Under.
There you go.
Together, when we do experimentation, we will understand why the spectrum of an object can be so informative. I believe it's like a fingerprint. Is this right, Gabriel?
Yes, it is exactly like a fingerprint. That is what's great about looking at spectra of stars in the galaxy.
Ah, these are signs from God. Interesting.
Fair enough.
Okay, let us continue. In the topics that follow, you will learn about the stars, galaxies, and the planets, often using rich information derived from their spectra to uncover the secrets of their internal structures and stories. Very exciting, Gabsmack. I look forward to learning about this with you.
Oh, it's a pleasure. So, there you go. Now we're going to talk about light and telescopes. How's that? You guys want to talk about light and telescopes? Young Black Chief. Hey, 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 Young Black Chief, welcome.
Telescopes. Hello, young Black Chief. Lovely to see you. Telescopes gather and focus light. So you need to study what light is and how it behaves on your way to understanding how telescopes work. You will learn about telescopes that capture types of light not visible. Boring! This Bumpus is a very impatient.
Keep going, my friend.
You will learn about telescopes that capture types of light not visible to the human eye, such as radio waves and X-waves. X-rays, I'm sorry. Can't read, can you? Okay, Bumpus, you need to be quiet before I chew your face off. These enable astronomers to put together a more complete view of celestial objects. You want to talk about quanta and refractions. I believe Gabsmack will talk about this in the quantum mechanics lecture. The science of astronomy is based on observations. Astronomers cannot visit distant galaxies and far-off worlds. Oh, really? I did not think that that was obvious. So they have to study them using a telescopes. Hello, Sweden. Hello, my friend from Sweden. I believe Sweden, they speak Arabic there. Is that not right?
I think they do in some parts here.
Interesting.
All right. So let us move on Now we're going to talk about radiation and information from space. Mufasa.
No, my name is Al-Asad Al-Mustafa. Close to Mufasa, but Al-Mustafa.
I just call him Al-Assad. In astronomy, we cannot perform experiments with our objects, planets, stars, and galaxies. The only way to investigate them is by analyzing the light and other radiation which we observe from them. Second most spoken language is indeed Arabic in Sweden. Well, congratulations to the new world, my friends.
I am very proud to hear about this. Al-Asad, no, I am not from Sweden. I am from Saada. It is a beautiful place. It is not from your world. It is from my world. The same as Pompous. Yes, I come from the same world as Pompous. It is very interesting to observe humans.
Interesting stuff, isn't it? So, I'm going to bring you guys to my friend Eagle. Let me introduce you to Eagle. Eagle is another guy. He wants to read as well, so he's going to read to you guys. Excuse me for a moment.
Hey guys, I'm Eagle. Great to meet you all. Where are you from, Eagle? I am from USA. Oh yeah. Ah, you are from the Great Satan. What?
It's all right. Don't worry about him. Different mentalities.
Okay, let's move on. Let's talk about light. Hey there, Supernova. Great to meet you, gorgeous shades. Oh yeah.
All right, excuse me for a moment while I bring up the next lecture slide. All right, you ready to read?
Sure.
All right, let's do it.
Okay. Light as a wave. Light waves are characterized by a wavelength lambda and a frequency f. Fu! Pompous, go away. F and lambda are related through c. What's c, Gab?
Oh, c is the speed of light.
Okay, so the wavelength multiplied by the frequency equals the speed of light.
That's exactly right. Well done.
Interesting. That's pretty cool.
Yeah, it's not too bad, is it? Alrighty, so that was Eagle. And now we're just going to talk about the next thing. Light as a wave. Wavelengths are measured, right, in units of nanometers, right, or an angstrom. So 1 nanometer, W by F equals C, close. Yes, wavelength, but it's spelt lambda.
It's lambda, you dopes. What's a lambda?
You just called him a dope. You don't even know what it is.
Fine. I caught myself in my own hypocrisy. What you going to do about it?
Pompous man. He just wastes time, I tell you. So, 1 nanometer is 10 to the minus 9 of a meter. That means 10, right, with 9 zeros. So, it's sort of like the inverse of a billion, in a way.
Whatever. Move on.
All right. So, visible light has wavelengths between 4,000 to 7,000 angstroms.
Angstroms? What type of stupid name is that? Why? Why don't they call it Ang weak?
It's not strong, it's strom. It's angstrom. It is named after some guy who I believe was German or Swedish or something. I think Michael would know about that. Where is Michael? Is he still here? Let's have a look. Yeah, he is. He's still here.
Of course he's here. Where else is he going to be? Goodness me, Gab smacked.
Anyway, so this rather Sweden. There you go. So 1 nanometer, 10 to the minus 9 of a meter. Okay. Al Swedish. 1 angstrom, 10 to the minus 10. 0.1 of a nanometer. That's 10 to the minus 9 of a meter. So it takes 1,000 of these to make a millionth of a meter. I'll explain that again. It takes 1,000 nanometers, 1,000 nanometers to make a millionth of a meter. right? So 1,000th of a meter, which is the reverse of doing 1 kilometer, right? So instead of doing 1,000 meters, you go backwards. You say the inverse, 1,000th of a meter, 1,000th of that, 1,000th of that, right? So it's 1,000th of 1,000th of 1,000th of a meter, and 1 meter is approximately 3.3 feet. Okay, so that's wavelength of lights. All right, light, as people know, can appear as both particles and waves. All right. So Al-Assad wants to talk about this.
It can be particles and waves. This is very, very interesting, my friend.
Yeah, it can be light and it can be particles and or waves. It's actually both, right? What's interesting is that a photon has a specific energy.
It has a specific energy. This is very interesting.
Yeah, we talk a lot about the wave nature of photons and quantum particles in my quantum mechanics lectures, but this is just astronomy. So hc over lambda, okay, h, right? H is the size of a pixel of this universe, and h times the speed of light divided by the wavelength equals the energy of the particle. Okay, so obviously if the frequency goes up, right, the energy goes up. So the energy and frequency work together. Okay, so have a look there. hc equals, so h is the pixel size of the universe, and that's the number 6.626 by 10 to the minus 34, right? So that is a million and 10,000. So basically a pixel is sort of like a millionth of 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 a 10,000th, right, of a little unit. That's how small the pixels are that make us up in this universe. So we're pretty high resolution. It's called the Planck constant. The energy of a photon does not depend on the intensity of light. That's quite interesting, isn't it? So if light has increased intensity, so if you shine a higher light beam, right, but it's the same wavelength, the energy of the photon does not increase. It just means that there's more photons. That's all. So that's quite interesting, huh? Okay, wavelengths and colors. Colors of visible light correspond to different wavelengths, right? I think a lot of people know this stuff already. So, need satellites to observe, high-flying airplanes or satellites, right? And just to show you the whole spectrum, we only see like that much of the whole spectrum. Have a look at this. Okay. So this is the whole spectrum, and this tiny spectrum, right? This section is what we see. We see this little spectrum. All the rest are observed by other instruments. So our eyes and brain don't even pick them up. That's how sort of backwards we are. All right. Just by analyzing the light, to apply to NASA, nah, something about working for the government I don't think would work for me. Just by analyzing the light received from a star, I was kicked out of my scholarship actually, even though I did nothing wrong. But you know, we know what there seem to be a lot of communist sections, totalitarian, ideological based institutions now in science, unfortunately. So, just by analyzing the light received from a star, astronomers can retrieve information about a star's 6 things. They can get total energy output of a star, the surface temperature of a star, the radius of a star, the chemical composition of a star, the velocity relative to Earth. Hey, Mr. Abyss is back. And the rotation period. So how many times it rotates per second or whatever, or per certain time period. All of that, 6 things you can get. Yeah, Redshift. Hey, Abyss, young black chief. I like a young black chief. Knows his stuff. All right. Welcome back, Mr. Abyss. This will probably be too advanced for Mr. Abyss. Photons are my distant cousins. All right. So, an atom, right, consists. Now, this is different. When we talk about quantum mechanics, Atoms are completely different to what we're talking about here, right? But here, by the way, I have to talk about this in one of my quantum mechanics lectures. But antimatter is actually matter traveling backwards in time, which is very interesting. But we won't get into that in this lecture. We've got to talk about that in the next lecture. Um, an atom consists of an atomic nucleus, yeah, protons and neutrons, and a cloud of electrons surrounding it. Antimatter matters. Almost, oh, sorry, I'm getting uncomfortable. I'm sitting on my couch. I sleep on a couch, by the way. Almost all of the mass, I'm actually pedaling as we're talking. I think I've done like 450, 500 calories so far. Um, Almost all of the mass is contained in the nucleus, while almost all of the space is occupied by the electron cloud. So here's the thing. If you took all of the matter in the Empire State Building, my head hurts, yeah. So just one electron in this universe. Ah, Mr. Deltron. Someone watches PBS Spacetime. No, that's probably not true, but it's funny to think about it. If you took the Empire State Building and you took out all of the space between all the atoms and the electrons and just got rid of all of the space within each atom, one electron theory, yeah. Do you know, have a guess how big the Empire State Building would be if you took out all of the gaps within each atom between the electrons and the neutrons and the protons? How big would it be? Would it be the size of a house, the size of a car, or the size of a golf ball? It's a trick question. It would be even smaller than all of those. Smaller than a pin. Mr. Black Chief, probably like micrometers. Mr. Rabis, the size of a rice corn, National 90, exactly right. That just shows you how much space. If you had a stadium, right, the whole stadium would be like the atom, and the nucleus would be sort of like a little, a little seed in the middle of the stadium. All right. Now they talk about an electron cloud, right? We're going to look at it in astronomy. We look at atoms as if they have an electron cloud. But what's really going on in quantum mechanics, we know that the electron doesn't really exist in a way. It's more just an interaction with a field, and it can only exist at certain points, like a computer software. You can't have pixels in between. Anyway, if you could fill a teaspoon with material as dense as the matter in atomic nucleus, it would weigh 2 billion tons. 2 billion tons, right? So basically, yeah, it would sink right through the Earth. It's a probability. Yeah. Different kinds of atoms. The kind of atom depends on the number of protons in the nucleus. Right? Most abundant is hydrogen. That's why dark matter and neutrinos can pass through without being affected. Dark matter, well, dark matter, the hypothesis is yes, you're dead on, right? But no one can prove that yet. With neutrinos, it's not just the fact that it's space, but yes, it's mostly because of that. It's another thing because it doesn't react as much with other elementary particles. Dark matter is an exception, yeah. It's funny, it's an exception, but it's sort of like 30% or 26% of the universe. All right, so the universe is mostly hydrogen, and the next is helium. What a coincidence. Do neutrinos have mass? They do have mass, yes. Electron orbits. That is why neutrinos can't travel at the speed of light. They can travel at 99.999% of the speed of light, but not the speed of light. All right, so electron orbits in the electron cloud are restricted to very specific radii and energies. Right? So this is quite interesting, right? They have very specific energies. And when you give it energy, it will not jump to the next one until it gets the exact energy, and then it will just appear. It doesn't. Right, so have a look at this. So this is hydrogen. With hydrogen, this is the energy levels. Okay? And it just goes ping, ping, ping. It doesn't travel in between at all. There is no such thing as the space. Here is helium, right? And then here is, it should be boron. Yeah, it is. It's boron. So, all right. So these characteristic electron energies are different for each individual element. And that's obviously brilliant. It pops in and out, exactly. And it pops in and out. That is a bad joke. All right, so that is why it's easy to fingerprint stars based upon their electromagnetic waves that get to us, because each star has a fingerprint based upon the energies that it can emit depending on what it's made of, right? So basically, the type of electromagnetic radiation or light, right? Atomic spectroscopy, exactly. So you need the like a belly button, pretty much. Yes, that's a better version of what I was thinking. All right. So what was I saying? It can be kicked. Okay, so you need to give it the exact amount of energy to kick it up to the next level. And if it does not react to the level that you give it, then it's not the particle you thought it was, right? So the photon is absorbed and the electron is in an excited state. Woo! All other photons pass by the atom unabsorbed, right? Because if it's not exactly the right one, it won't get absorbed. All right. So the Rigel star or Regal, what's an electron mode? Ooh, electron mode. Electron mode. Did you mean electron model? I don't know what electron mode is. All right, so stars appear in different colors from blue, right, to green yellow like the sun, or red like Betelgeuse. Okay, these colors tell us about the star's temperature. Betelgeuse is gigantic, by the way. Betelgeuse, like our sun, is like this compared to like Betelgeuse. Like, can you imagine? Imagine that, having that in the sky. Black body radiation. This is where quantum mechanics begins. What's interesting is that we used to think before quantum mechanics and Niels Bohr and Maxwell and stuff, we used to think that when you shine light inside an object, it should keep reflecting to the point where it just heats up and then the whole thing just lights up. But it doesn't happen that way. And the reason is because we live in a pixelated universe. This pixelated universe means that every single thing has a certain resolution dimension. So we know that lights occupy a certain amount of resolution, right? How many pixels? So the light from a star is usually concentrated in a rather narrow range of wavelengths, very specific, like fingerprints. This spectrum of a star's light is approximately a thermal spectrum called a black body spectrum. A perfect black body emitter would not reflect any radiation, thus the name black body. The metallicity of the stars also affects their colors too. Absolutely, my friend, absolutely. 2 laws of black body radiation. All right, so here are the 2 laws. Hey, folk music, back to answer more questions. All right, so your star student. All right, so let's do this. So we have here that the peak of the black body spectrum shifts towards shorter wavelengths when the temperature increases. All right, so we have here Wien's displacement law, or Wien, like Wiener. What a Wiener. All right, here we go. So where T is the temperature in Kelvin. So Kelvin is absolute temperature. So 0 Kelvin is theoretically absolute zero. Nothing can exist colder than that. And in fact, nothing can exist at absolute zero either that we know of. Nothing can exist. Minus 273.5 or whatever it is. Yeah, exactly. So have a look at this. I'm the star student. It's on. All right, so lambda max equals 2.9 by 10 to the 6 nanometers in Celsius. Yeah, exactly. Well, basically, yeah, Kelvin and Celsius are linearly related. 1 to 1, yeah. We can both be alpha students. All right, over T, which is the temperature. Okay, so the higher the temperature, right, the higher the max wavelength, right? So sorry. The higher the temperature, the lower the wavelength. So it's an inverse relationship. Alrighty, let's keep going. 2 laws of black body radiation. The hotter an object is, right? We're going to do tests on this later, right? The hotter an object is, the more energy it emits. Where E is energy flux. All right, flux is an interesting concept because it works over the surface area. So basically it's like if you have a meal, if you have soup, right? If the soup is in a cup, it takes longer to get cold than if you put it in a plate, and it has a lot more exposure. Flux capacitor. Marty! Hey, Doc! We gotta go back! Marty, great Scott! Okay. Alright, so I'll show you energy flux. Alright? Energy flux, you can see the focus, I know. That's my worst thing. I'm very bad at focusing. All right, so flux, and that's the flat surface, and that's the energy coming up. And that is why it is theta t to the power of 4. Right? This is a Stefan Boltzmann constant, so that's just a constant of this universe. This universe has this constant. Energy given off in the form of radiation per unit time, per unit surface area. Okay? So that's why the temperature is to the power of 4, because you have 4 dimensions. You've got the 3 dimension of space and time, so that gives you 4 dimensions. Joules, second, and squared meters, basically. Okay, so stellar spectra. The spectra of stars are more complicated than pure black body spectra. What I said about the time and the space, that's not actually correct. That's an analogy to give you an idea, right? Why it's temperature to the power of 4. I keep getting messages, man. All right, the spectra of stars are more complicated than pure black body spectra. The sound has gone strange. Whenever I get messages, there starts to be a delay in the speech and the audio. I don't know why. And I've blocked the messengers and I still get them. You sound like a Dalek. A Dalek? Hey, Dalek. All right. They contain characteristic lines called absorption lines. With an understanding of atomic structure, we can now understand how these lines are formed. All right, so let's go to Kirchhoff's laws of radiation. You can hear me fine? That's because you are the abyss, my friend. All right, so folk music is back. A solid, liquid, or dense gas excited to emit light will radiate at all wavelengths and thus produce a continuous spectrum. Okay, so that's actually quite interesting. Hey, welcome back, my friend. All right, so a solid, liquid, or dense gas, yeah, excited to emit light. Okay, if you excite that gas to emit light, it will radiate at all wavelengths. All right. So if you give it enough energy and it glows, it'll glow. So you have a look, right? So that's the light, right? Like a light bulb. It shoots out into the telescope. And then we get the spectrograph here, which is exactly what Abyss was talking about before. And you got the continuous spectrum. Alrighty, so we're getting somewhere. Right? And now, let's see how many lectures we are in. Oh, we're halfway. Very good. Okay, Kirchhoff's laws of radiation. Okay, the next one. A low-density gas, ding! A low-density gas excited to emit light will do so at specific wavelengths and thus produce an emission spectrum if the gas is low density. All right. So, and here's the next one. Here's the next law. Neon. Yeah, if it's at low density, you'll get neon lights, but they don't actually use neon anymore in neon lights. They use like, I don't know, some argon or something cheaper. If light comprising a continuous spectrum passes through a cool low density gas, the result will be an absorption spectrum. Noble gases, yep. Yep. And what's interesting, the reason this is interesting is because when you combine the two, when you combine the two, right, you know that a light globe, for example, emits light on the whole thing. If you put a gas in front of the light, then that gas, kryptonite, yeah, is gonna absorb some of that light and let the rest go through, right? So this is what happens. Let me show you what's going on. Right? So here is the light. It shoots out light, but there's the gas around it, so it sort of gets smacked around, and what gets left is a certain spectrum, so you might only get a certain amount of colors. And the reason that's important, obviously, you've probably figured this out. The reason that's important is so that you can tell what gas is around the object, right, that's emitting the light. Okay, the spectra of stars. The inner dense layers of a star produce a continuous blackbody spectrum. Cooler surface layers absorb light at specific frequencies. That's really interesting, actually, because that means that that's how you can tell, right, the surface and the subsurface of the stars, because the light coming from inside the star in the core, as it comes out, exactly what Abyss actually, once again, Abyss was saying before, where you can see the metallic structure of the star as it comes into the lower density gas sections on the outside, like the helium and the hydrogen, as it goes through that gas part of the light gets absorbed, so we only get a bit. And that's why different stars have different colors, because they have different densities of gas, right? And different gas makeup. So I'll show you right here. Lines of hydrogen, most prominent lines in many astronomical Balmer lines of hydrogen. Escaping photons from the core excite gas. Yes, that's exactly right, my friend. Exactly right. Different stars have different bands. Yeah. Different bands and different brands. Some of them want to make space great again. It's a terrible joke. All right. In many astronomical objects, Balmer lines of hydrogen. Okay, Balmer series. Okay, visible light spectrum. This is quite interesting. So what it does is that it excites at certain levels, only at these levels, right? And it'll skip to those levels. So you can, that's like the fingerprint of hydrogen gas, right? And this is the Lyman series. So this is the fingerprint of UV, and here's the nucleus, right? And here is the Passion series, which is a completely different series as well, but we'll get into those later. The Balmer is the most common, and it's very easy. It's very easy to work stuff out. All right, so the Balmer lines, all right? So the only hydrogen lines in the visible wavelength range, right, are n equals 1, 2, 3, 4, and 5. And they work, so for example, you've got the Balmer alpha line and the Balmer beta line. Obama lines. That's pretty cool. Yeah. So, all right, here are the Obama lines. And this is the hydrogen lines. So that's hydrogen alpha, right? Which goes from 2 to 3. But then you've got beta, which goes from 2 all the way to 4, right? And then here, second to high level hydrogen, that's a pretty big whack. Observations of the H alpha line. All right, emission nebula dominated by the red H alpha line. All right, and you can see like it's red if you look at it. So clearly, just by looking at it, you know what type of gas is there, right? Absorption spectrum dominated by Balmer lines. Balmer dominates, my friend. All right, so intensity and wavelength. Modern spectra are usually recorded digitally and represented as plots of intensity versus wavelength. All right, which is quite interesting. Clearly, the intensity is higher for the higher hydrogen Balmer levels, right? So the first level is not much excitement. If you get really excited, then it goes all the way up to like, alpha, beta, gamma, delta. I wonder if isotopes of hydrogen have different spectrometric fingerprints. They do, my friend. They actually do. That's a very good question. They actually do. Okay. Isotopes. I'll show you actually. Different S spectra. All right, so isotopes and mass spectrometry, there it is. Just loading it up, sorry about that. So that was a really cool question. That's like, as always, Abyss asks questions that are way too advanced for the subject, but it's always a pleasure. All right, so atomic weights. Okay, so the relative abundance of each isotope, right, can be determined using mass spectrometry, which we're not going to do in this thing. A mass spectrometer ionizes atoms and molecules with a high energy electron beam, and then deflects the ions through a magnetic field based on the mass to charge ratio of the ion. All right, the mass spectrum of a sample shows relative abundance of each ion on the y-axis. All right, so yes, we're not gonna get into that, but yes, it is. You absolutely can discover it through spectroscopy. Let's get back. Alrighty, so the Doppler effect. Everyone knows the Doppler effect. It's like, you know what I mean? Yeah. All right. All right. And of course, light does the same thing, and that's how we can find the velocity, right? And you guys remember, we did some of this in the assignment. We talked about if a wavelength was coming from Mercury and it was like 9 inches long, and that was a pretty bad joke. So you can find the radial velocity, and so obviously the velocity coming away or from us, right? And then you got to find the actual wavelength. So there's a pretty cool formula for that, right? VR over c. So the radial velocity divided by the speed of light, right, is the same as taking the change in the wavelength over the original wavelength, and you get the same, right? So that's pretty cool. So what are we up to now? All right, Doppler effect. Doppler effect allows us to measure component of the source's velocity along our line of sight. This is pretty awesome, right? So it doesn't give us the actual velocity. It just gives us the straight component of the velocity. So if the star is not moving away from us, maybe it's moving on an angle. If it's moving on an angle, we're not going to pick that up. We're only going to pick up the speed that it's going away from us. So it's like if you're standing here and there's a car not coming towards you, if it's going like diagonal, right, you're not going to get its speed in the diagonal direction. You're only going to get its speed relative to you. So then you have to figure out its distance that way and then use trigonometric mathematics to calculate what its speed is in that direction, which is pretty cool, right? And it's really interesting because as Earth's orbit, as we move in our orbit, you know, we go away and sort of, even though we go in a circle, you can convert that using trigonometric functions. It's a lot of work, yeah. Yeah, it's a lot of maths basically, and that's the fun part. That's the part I enjoy. But computers do it all these days anyway. But right, that circle, you can translate that into perpendicular motion, right? Into a spring motion, like forwards and backwards. And so as the Earth moves away and moves forward, the color of the galaxy changes that we're looking at. Right? Okay, the Doppler effect. Okay, so here's something interesting, right? The wavelength of the Balmer alpha line, right, is 656 nanometers. So 656 multiplied by 1,000th of a billionth of a meter, right? But what happens is that the line can change by 2 nanometers. Isn't that crazy? 2 nanometers. So 2 multiplied by a billionth, 1,000th of a billionth. Is that right? Now, hold on a sec. I've stuffed something up. Sorry. No, sorry. I'm wrong. It's 2 times a billionth of a meter. So 1,000th of a millionth of a meter. Sorry, I stuffed that up. All right. So we find, look at this, right? The change in light wave, right? When looking at a star that's next to us that might happen to be shifting a bit, right? It's 0.003, right? Is the difference. And so when you multiply that by the speed of light, which is 200,000 miles per second, then you get the speed of 900 kilometers per second. So what's that? That's like 654, like 500 miles per second is how fast the light is going, and it's going away from us because it's red shifted, so it's stretched a bit. Okay. The larger the telescope, the more light it can gather, obviously. And this is pretty cool. Like they have them on top of mountains into space. I love this stuff. Look at that. How crazy is this? And that's the clouds on top. I think that's the Andes Mountains, isn't it, in Chile? Someone will probably know that better than me. Why is this stuffing up? Freaking hell, this Windows PCs, man. Honestly, it's just crazy. All right, refracting and reflecting telescopes. Buzz Lightyear or Bud Light? I may have to be forced to convert to an Apple, as much as I don't like them. All right, refracting, reflecting telescopes. Are any of my Patreon supporters here? Nope. All right, so this is pretty cool the way it works, right? So what they do is you can put the focus here and make it bend that way. That's a reflecting telescope. This is a refracting telescope. Refracting is where the focus is here and it goes through there and then squeezes it that way, as opposed to squeezing them back this way. And you can see the shape of the lens is different, right? This here is concave and that's convex on either side. That's a double-sided convex lens, sort of like an eye. secondary optics. This is pretty cool too. In reflecting telescopes, secondary mirror is required because obviously it reflects back and then back there, then back to you, right? Where this one, you don't eyepiece to view and enlarge small image produced in the focal plane. So that's actually different. That one here, you have to enlarge that from the focal image and it shrinks it there. This one here will probably have much more power, I'm guessing, because of the increased distance. Disadvantage, the way these telescopes adjust for atmospheric refraction is an amazing engineering. Oh, it's insane. Yeah, the mathematics, man, it's crazy. Chromatic aberration. Different wavelengths are focused at different focal lengths, prism effect. So this is the problem with refracting telescopes. So you're going to get a little blur of color on the edges. It can be corrected, as Abyss was saying, right? Oh, freaking hell, right? But not eliminated by second lens out of different material. Difficult and expensive to produce. All surfaces must be perfectly shaped. Glass must be flawless. Okay. And to actually hold the lens in the telescope, it has to be at the edge. So they're so expensive. If you knock it, it's all gone, mate. It's all over. All right. So you need to catch the area. And the area obviously is related to the, what do you call it? The discovery of the relationship between the radius of a circle and its area, and that's simple. That's from high school mathematics, pi r squared, which is interesting because the mathematics is actually more accurate than the measurements because we live in a pixelated universe, but maths is infinitely small, right? All right, resolving power. So we've got something called resolving power. I might end the lecture here and I'll make a part 2 next time, I think. You guys interested in just leaving that here and we do another one next time? Or what is it that you would like? What would you prefer? Let's see what, because we're about 60% of the way through. So if you want, we can take a break. When the mirrors misalign, the images will blur. Yeah, that's right. Yeah, exactly. Yeah. Well, I think I will stop here and we might do the next lecture tomorrow. We can break. Yeah. Thank you. I'm half dead. I got to go to sleep because I'm going to get up at 11 o'clock tonight, our time, which is in another 5 hours. And then I'm going to work until the morning. So until we get enough Patreon members, that is what I will do. Lovely to see everybody. Are you a professor? In my dreams. No, I am a very successful student. Gab got to turn in 347. Jesus, go to bloody sleep. Get out of here, man. Gabversity, facts, don't care about your feelings. Love you all. And thanks to Patreon, thanks to GoFundMe, to all of my guys from my other channels. Love you all. All right. Always a pleasure. It's nothing without you guys. Bye-bye.